Welcome to Central Limit Theorem and its applications. In this hands-on Python session, we will explore the Central Limit Theorem, CLT. See why it is a cornerstone of statistics, and test its power with simple experiments. Let us break down complex ideas and use real-world data so you see how theory meets practice. Running the cell now. Let us start by making sure nothing interrupts us with warning messages. We are blocking warnings so your notebook stays clear and distraction-free. Running the cell now. What is the Central Limit Theorem, CLT? CLT says, no matter what your population looks like, if you take lots of samples and average them, their means will look like a bell curve, a normal distribution, as your sample gets big. This is why averages of things, like average test scores, average heights, tend to follow a normal pattern, even if single measurements are not normal. Running the cell now. Let us set up our environment. We are importing the tools we need for math, data tables, and making charts. Setting the random seed lets us get the same random numbers every time, which is great for learning. We are starting by importing NumPy for number crunching, Pandas for tables, Matplotlib and Seaborn for plots. We set the random seed so our results match every time. Running the cell now. We will make up a fake population, like a city of 10,000 people. Instead of using real income data, we use an exponential pattern, which is not bell-shaped. This shows off the central limit theorem better. Let us also check the average and the spread. We are making a fake population that is very skewed to the right, like incomes often are. We use an exponential pattern to make most incomes small and a few very large. We print the average income and how spread out the incomes are. Running the cell now. Here we visualize our population to see how it is distributed. We are drawing a histogram, which counts how many incomes fall in each range. We are using 50 bins to see the shape more clearly. We add a title describing what we are looking at. We label the horizontal axis as income. We label the vertical axis as count. We display the chart. Running the cell now. Notice how most people have low incomes and only a few have higher incomes. The shape is not a bell curve yet. What happens if we take just one sample? If we pick just a few people, their average might be very far from the true average. Let us see how that works. Running the cell now. Let us randomly pick 5 incomes from our population. We will see what these incomes are, and what their average is. We are drawing a small sample of incomes from the big population. We print the 5 sampled incomes. We print the average income for just these 5 people. Running the cell now. Notice how the sample mean can bounce around a lot when the sample is tiny. What does the central limit theorem say? It says that as we take more samples of the same size and plot their means, the distribution of those means will look more and more like a normal curve. Running the cell now. Now we will do lots of tiny samples, 5,000 of them. Each sample takes 5 people, finds their average, and saves it. Then we will look at what all those sample means look like. We are drawing 5,000 random samples, each with 5 incomes. We are storing their averages in a list. We make a histogram of all these sample means. We show the shape using orange color and a smooth curve. We write a title to explain. We label the axes. We display the plot. Running the cell now. Can you see that the shape is starting to get smoother? But it is still not perfectly normal with such a small sample size. Let us try the same experiment, but with samples of 30 people. The central limit theorem says bigger samples should make the means look even more normal. We are drawing 5,000 samples, but now each sample has 30 incomes. We are saving each mean just like before. We show a histogram of these bigger sample means. We use green to tell them apart. We give a title and label the axes. We show the chart. Running the cell now. See how the distribution is getting tighter and smoother? Big samples make the bell curve even clearer. Summary of what we see. When you take small samples from a weird population, the averages can jump around. When you take more and bigger samples, the means act normal, like a bell. This is the magic of the central limit theorem. Running the cell now. Now you get to pick your own sample size. Type 10, 50, or 100 when asked. Let us see what happens. We ask you for a sample size so you can experiment. We set 3,000 samples for this mini experiment. We find the average for each sample and collect them. We draw a histogram of these means. We make it purple so it stands out. We use a dynamic title showing your choices. We label the axes clearly. We display the plot. Running the cell now. Try a few different sample sizes and notice how the shape of the means gets closer to a bell curve as your sample grows. Would you like more hands-on walkthroughs like this? Subscribe so you do not miss the next lesson. Let us compare the real population mean and the typical mean of your samples. We also see how spread out the full population is versus your sample means. This helps you see the central limit theorem in action. We show the average of the whole population for reference. We show the average of your sample means. Next, we compare how spread out the incomes are in the full population. And finally, we look at how much the averages of our samples bounce around. Running the cell now. See how the sample means cluster much tighter than the wild incomes themselves? That is why averages are so predictable. Now we will use a real-life data set of restaurant tips. Let us load this data and peek at the first few rows and shape. We are loading the tips data set from Seaborn, which records meal bills and the tips left. We print the shape, which means rows and columns. We show the first 5 rows, giving you a sense of the data. Running the cell now. This data set includes bill sizes, tip amounts, day of week, and more, real evidence for our statistics. Let us look at the shape of the tip amounts in the data. We make a histogram of all the tip amounts. We draw a smooth line to see the shape more clearly. We use 30 bars to show more details. We set a helpful title. We label how much the tips are worth. We label how many times each tip amount appears. We show the figure. Running the cell now. Tips are not perfectly normal. There are lots of smaller tips and only a handful of large ones. Now, let us pretend we keep picking random groups of 25 tips from our real data. We do this 2,500 times, each time saving the average. Then we will see the shape of all those averages. We are drawing 2,500 samples from the tips data, each with 25 tips. Each sample's mean is saved for plotting. We plot a histogram of these sample averages. We use a clear color and smooth line. We give the chart a title. We label the axes so it is easy to interpret. We display the plot. Running the cell now. No matter the original shape, the average tips create a distribution that is nearly bell-shaped. Try making your own tiny sampling project. Can you think of something fun to measure the averages of in daily life? Best practices and troubleshooting. If your samples seem odd, check these. Make sure you are sampling randomly, not in order. Use enough samples, a few hundred at least. If your code is slow, lower the number of samples. When in doubt, Plot what you are sampling. Getting weird errors? Try running the cell again, or double-check your brackets and parentheses. Running the cell now. Here is a tip to impress friends. Let us put histograms of sample means for 3 different sample sizes side by side. Notice how the shape gets more bell-like with larger samples. We make 3 charts in one row, for sample sizes 3, 10, and 50. For each size, we draw 2,000 samples and plot the average each time. We use steel blue for the bars and put a title on each. We set the axis labels for clarity. We adjust the chart so nothing overlaps. We show the big picture. Running the cell now. Look for the transformation from lumpy to smooth as sample size grows. Try changing the numbers and see what happens. For your mini-project, let us simulate rolling a die lots of times. We treat the possible outcomes as our population. We will take many samples of 20 rolls, record the average, and then see what kind of distribution appears. We make a huge virtual population of dice rolls. We pick 20 at a time, over 3,000 samples, and find their averages. We save those means for plotting. We make a histogram with gold bars to show the result. We add a title and label the axes. We display the result. Running the cell now. No matter what real-life or toy data you use, the central limit theorem appears when you average enough random samples. Now for a challenge activity. Use the tips data again, but focus on the total_bill column this time. See how the distribution of averages looks when you repeatedly sample 40 bills at a time. We take 1,500 random samples, each with 40 total bills from the dataset. We compute the average for each and save the results. We draw a histogram to see how the sample means are distributed. We use tomato red so it stands out. We add a clear title. We label both axes. We show the plot. Running the cell now. Notice the normal look, even though a single bill can jump around, the averages settle into a predictable bell. Recap, key takeaways. The central limit theorem helps us trust averages. No matter the original shape, averages of lots of samples turn bell-like. This makes statistics powerful for science, business, and understanding daily life. Keep practicing sampling and watch those bell curves appear. Running the cell now. Thank you for learning with us. If you enjoyed this notebook or video, give it a thumbs up and subscribe. Keep exploring, and let the data surprise you. Running the cell now.